All right, let's talk about something that sounds like it's straight out of a movie. Hitting a bullet with another bullet. It's an idea that seems totally impossible, right? But the real science behind it is, well, it's even crazier than that sounds. So let's dive in.
You've probably heard that phrase before, right? Hitting a bullet with a bullet. It's the go-to analogy for missile defense because it perfectly sums up how insane the task sounds. But here's the thing. As you're about to see, that comparison, it doesn't even come close to the real challenge. Okay, so this is where that whole bullet analogy just completely falls apart. Look at these numbers. A rifle bullet, it's moving at about Mach 2.5. Fast, right? But a ballistic missile, we're talking Mach 16. That's over 20,000 kilometers an hour. So let's be real. This isn't hitting a bullet with a bullet. This is like trying to hit a lightning bolt with another lightning bolt.
So that's the big question, isn't it? With these just unbelievable speeds, how is this shot even possible? And we're not talking about a 1 in a million lucky shot. We're talking about doing it reliably, time after time when everything is on the line. And yet, they pull it off. I mean, look at this. In a recent 4-week period, out of about 1,000 Iranian ballistic missiles launched, an incredible 90% were stopped. 90%. That's not luck. That's a system. Which brings us back to the main question. How on earth is a success rate like that even possible?
Well, the answer isn't some kind of magic bullet, or, a magic interceptor. The secret is a much bigger strategy. It's all built around this idea of a shield that's made of multiple layers.
So the core idea here is something called layered defense, and it makes a lot of sense when you think about it. There's just no single system that can handle everything, from a tiny little drone all the way up to a massive long-range missile. So countries build their shields in layers, kind of like an onion. Each layer has a specific job, designed to take on a very specific kind of threat.
And a fantastic real-world example of this is Israel's air defense system. You've probably heard of the Iron Dome, right? Well, that's actually just the inner layer, the one that deals with short-range rockets. Then you've got David's sling forming a middle layer, and way up high you have the Arrow system, which is the outer shield. It reaches way up into the upper atmosphere to take out threats while they're still far, far away.
Okay, so we've seen the big picture strategy. Now let's zoom way in. Let's look at the split-second timeline of just one of these interceptions. What actually goes down from the moment a hostile missile is launched?
So it doesn't matter what system we're talking about. Every single interception breaks down into these 3 basic steps. First, you've got to detect the threat. This is done with incredibly powerful sensors, like phased array radars that can track tons of objects at the same time. Step 2 is decide. A command center has to analyze the data, confirm it's a threat, figure out where it's headed, and calculate if they can even get to it. And then, finally, step 3, intercept. That's when you launch your own missile to go meet it.
And to put this into perspective, let's look at the US Patriot system. A single battery, which is just the smallest unit that can operate on its own, is basically a self-contained defense bubble. It's got everything it needs: its own advanced radar to do the detecting, a control station to make the decisions, and of course, the launchers that fire the interceptors.
Okay, so we've got the strategy and we've got the steps, but we still haven't really answered that core question, have we? How does an interceptor, screaming through the sky at thousands of kilometers an hour, actually manage to hit a target that's moving even faster? Well, the answer? It's just pure elegant mathematics.
This right here, this is the heart of it all. This is the multi-billion-dollar question that literal geniuses have been working on for decades. How do you solve what seems like an impossible physics problem and do it in real time?
First things first, let's bust a common myth. The interceptor is not just playing a game of catch-up. It's not just aimed at the target and chasing it across the sky. See, if it did that, it would almost always get stuck in what's called a tail chase. It would be constantly turning, bleeding energy, and 9 times out of 10, it would miss, especially against something moving faster than it is.
No, the real solution hinges on a surprisingly simple concept called the line of sight, or LOS for short. All it is an imaginary straight line drawn between the interceptor and the target at any given moment. And believe it or not, that line is the secret to this whole thing.
And this is where the genius comes in. The interceptor's onboard brain, its guidance system, it only has one main goal: keep that line of sight's direction constant. As it's flying, it's constantly making tiny adjustments to its own flight path just to make sure that angle, relative to a fixed point in space, never ever changes.
So why is that so important? Well, it's simple geometry, really. If the interceptor can manage to keep every new line of sight path parallel to the very first one, then the laws of physics and math say their 2 paths have to cross. It's a guarantee. By holding that constant bearing, they are absolutely going to end up in the same place at the same time.
I think this quote just nails it. The interceptor isn't chasing anything. It's maintaining a geometric relationship. If the geometry is right, the hit is inevitable. It's not about brute force. It's more like an elegant, high-speed dance. The interceptor is basically a flying supercomputer solving a complex math problem. And as long as it gets the math right, that collision is a sure thing.
So now that we kind of get the mind-bending science behind it all, let's zoom back out and look at the bigger global picture. Because as amazing as this technology is, it comes with an enormous price tag and some pretty sobering realities.
And when I say enormous price tag, I am not kidding. Take a look at this. A single Patriot interceptor costs around $4 million, a single one. And if you go up to a THAAD interceptor, that's the high-altitude one, you're talking $12 million for one shot. You are quite literally launching the cost of a mansion into the sky every time you fire.
So what about the ultimate nightmare scenario? An intercontinental ballistic missile, an ICBM, carrying a nuclear warhead. What's the last line of defense for the US against something like that? It's a system called ground-based interceptors, and right now, the US has exactly 44 of them.
44. Now hold that number in your head and compare it to this one. Russia alone is estimated to have more than 1,700 nuclear warheads deployed and ready to go. The difference between those two numbers is staggering. And it tells you something really important. Missile defense isn't a perfect shield. It was never designed to stop an all-out nuclear exchange.
And that really gets to the heart of where the true strength of modern defense lies. It's not about any one missile battery, it's the network. You've got satellites providing the first warning, airborne command posts tracking everything, and ground-based radars all sharing data in real time. It lets all the different layers work together as one big, interconnected shield.
And that kind of brings us to our final, lingering thought. This technology is absolutely miraculous, there's no doubt about it. But the other side is always innovating, right? They're developing even faster hypersonic weapons and working on the simple strategy of just launching so many missiles that you can't possibly stop them all. And that leaves us with this one really critical question. In this never-ending race between offense and defense, can the shield ever truly keep up with the sword?